Hello, my name is Kenneth Bruni, and I decided to record this video to explain a few things as far as my solutions are concerned. So, what I ended up doing was, of course, I did the compulsory parts of the questions, question 1 to 4, and then for the section B, I worked on question 5 and then question 6 because those were the instructions to select 2. So I think these ones are pretty much straightforward, but then I would want to emphasize on the question 3, which needed a little bit of explanation. So what I did was I used LaTeX to do the formatting and everything. So I'll be presenting all the materials I have. So for question 3, as part of my solution, I had a graph and then the code for that particular visualization. And I believe to explain the concept of critical points, local minimizer, and global minimizer, it was necessary to have a plot so that the explanation becomes a little bit easier. So in the solution, what I have here is for a convex differentiable function, the relationship between the critical point, local minimizer, and the global minimizer is like that the critical point is equal to the local minimizer and it is also equal to the global minimizer. So I used this simple function to make my point. So f of x and y is equal to s squared plus y squared. And in order to make sense out of this, plotting this will make things quite easier for my explanation. So when you plot this graph, you are going to get something like this. Now, in the plotting, I also have here as, in order to find the gradient, we do the partial differentiation with respect to each variable. So in order to do that, then that's going to be the partial differential of the function with respect to x and also with respect to y. When we do so, this is a very simple function, so definitely when we do with respect to x, then the power over here comes down, so we are going to get 2x and then we subtract the power by 1 because that's the first differentiation, and that's exactly what we have over here. And then we do so for with the partial differentiation with respect to y, and that's exactly what we have over here. Now at the critical point, or the critical point occurs when the gradient is equal to 0. So after differentiating, we equate everything to 0, and therefore we have 2x is equal to 0 and then 2y is equal to 0. When we do the math, we end up getting these points, that's 0 and 0, and that's what we refer to as the critical point. So over here, this is a plot. Now in this particular environment, it is not going to help me explain exactly what I want to do. So what I ended up doing was I've provided a code over here. So I'll just copy this, Control C, and then I'll come into my other IDE. Then I'll come and paste it over here. So a brief explanation. This is more or less the function. So the function is x squared plus y squared. So in Python, the power or the squared, we use the double star. So we have the function, and then at the end of the day, we are returning this because that's the output. And over here, what I have is I'm going to run this code. So when I run this code, I definitely get this plot over here, and there's something I can grab and move around, and that's why I needed this. Now we are looking for the minimum point, and in this particular example where this is a convex function, we clearly see that it is almost like a bowl. So therefore the minimum point over here is certainly the global minimum and also the local minimum. It is not in a case where we have something usually like this. If we had something like this, then in that case we have 2 minimum points, and the one which is more minimum in some generic sense becomes the global minimum, and then the other ones becomes the local minimum. So in some instances there could be a number of local minimum points, but then the optimal or the global minimum is only one. Now we don't have this with this particular graph as we have plotted out over here, and for which reason that makes our explanation or my explanation very simple and concise over here. Now what I've also ended up doing is we have these red dots, where these red dots, if I'm to zoom in a little bit, this red dots, let me try zooming in over here. Let me go back. This red dots, oh sorry, this red dots, this red dots is pointing us to the minimal point, and if you are to critically look at this based on the calculations, we came up with the fact that the minimal point on the x-axis is 0. So clearly, if you are to even to do an eyeballing of this, we clearly see that the lowest point over here, as far as this graph is concerned, this on the x-axis is 0. And then if you are to move it around a little bit to look at what we have with the y-axis, we can also confirm that indeed also on the y-axis the minimal point is also 0 over here, and that explains the issue of it being the critical point. So if it is a case of a convex differentiable function, the relationship that exists between these part of that function is that the critical point is equal to the local minima, and then it is also equal to the global minima. Then with question 5, question 5a, for instance, where I'm supposed to solve for the actual question is here. So we have to compute for all the critical points of the function, and if there exists no critical point, we should state that. So I'll explain with the first particular function, or the first part of the question, which requires that, okay, basically all that we are doing is we have two variables over here, so we are doing the partial differentiation with respect to each variable, and then after doing that, that's essentially what we have over here. We equate everything to 0. So with this, the first, with respect to x1, if we are to concentrate on the terms that have x1 component in there, this is what we will be left with, and then when we differentiate or partially differentiate, that's what we get. Then in the case of x2, this is the only term, okay, and that's exactly what we have over here after the differentiation. So after that is done, we move on to now equating it to 0. So after the that particular process, we finally get that x1 is equal to 2, and then x2 is equal to 0. So that tells us the critical point after the first differentiation. In order to get more or less the global minima, because there's only the necessary condition, the sufficient condition requires us to do another differentiation, and that will lead us to the Hessian matrix. And when we do the second derivative, we find out that we get 2004 as far as the Hessian matrix is concerned, and this basically tells us that this is strictly a convex function, and that the critical point is 2 and 0, and it is a global minimizer. So in summary, we have the function or the parameters x1 is equal to 2, x2 is equal to 0. If you have to put this back into the function for our objective function to be minimized, then we are going to end up with 3 over here. Now once again, if I am to copy this, Control C, Control V, and let me call this test.py. If I'm to put this over here with this code, And once again, this is the function equation. So we have x1 squared minus 4x1 plus 2x2 squared plus 7. So when I run this, eventually, let me close this one before the new one opens. So we have this particular function being plotted out over here. And with this function, what I also have over here is that red dot that basically shows the global minimal point. So over here too, when we are to scroll along the axes that we have, we clearly see that on the x1 axis, we see that we are at 0.2, and then on the x2 axis, we see that it is at 0, as we can see. And with this visualization, it makes it very easy and very simple to explain the concept of global minima, and because it is very simple to see over here than just with functions. So that explains this short video that I have as far as the presentation of this work is concerned. The rest of the other ones, I believe videos wouldn't be necessary, so I'll leave it here. Okay, thank you very much, sir.